So I'm Harsha. I've been at Hortonworks for the last 3 years. So I've been working on Storm and Kafka for the last 3.5, almost 4 years, I guess. So recently we built Stream Analytics Measure, a new product in the streaming space. So I will go and do a demo of that. And before that, I'll try to explain what is streaming is, why it's necessary, what are all the projects that's been trying to tackle the problems in streaming space, and why we actually developed another project of streaming, because there are too many projects already in streaming space. Stop me anywhere, ask questions. So how many are know about stream processing or streaming, anything? Not Netflix streaming, but big data stream processing. Anyone? No. Okay, so streaming use cases, like if you use Twitter or Amazon, I'm trying to explain in terms of the use cases. For example, if you go to Amazon, right? So you are trying to buy a product, you're trying to buy a book. When you go to that book page, if you at the bottom of the page, you see people who already bought these XYZ books as well. So what's happening behind the screens is people are clicking all these items on Amazon, and they're getting bought, or they're getting kind of tracking the interest of the users. So there is a system at the back end taking all the events that our users are generating, like clicking, buying, or whatnot, and they're creating a model and processing it, and in real time updating the Amazon. So there is a continuous events that are coming through from the users, and those are kind of getting processed and making that into a recommendation model and appearing on the site itself. Similarly, if you go to Twitter, right? Twitter, you can say trending topics. There's an earthquake happen, there's an event happen, or there's something going on elsewhere in the world. So how do Twitter know what to showcase the trending topics? The way they do it is similar fashion. Is they run a engine like a Storm at the back end. So users are clicking, through the hashtags, through tweeting a location or whatnot. So all of that data is in real time going through this engine. So they are creating a window of that, last 1 hour, how many of the events are coming through, and they're kind of ranking them. So there are people talking about, let's say there is a football match, there's a tennis match somewhere else. They're tracking based on that, and they're propagating that data directly back to the Twitter website. So in real time, you're actually seeing the trends being changed across the world. So that's some of the use cases. Similarly, if you go to the stock program, right? So you want to know the latest news happening around any particular stack or Apple or Yahoo or stuff, so that you can analyze the stock better, you can understand what's going on. So all the news that are generating going through this pipeline, and an engine is actually processing that and giving the results back. The stream processing is nothing but there are continuous stream of events. So if you compare to MapReduce, so you have a big cluster of HDFS or whatnot. You have a static data that is being stored, and you might have a MapReduce that is running at a certain time of the day to process the data. Whereas streaming is always up to date. It's running forever. Like, the program is always running. There are events being generated. There are events being, calculated based on the incoming events, and results being generated. Right, so does that gives you an idea about what stream processing is? So little bit of history of streaming. So one of the popular projects that is started is Apache Storm. This actually developed, not developed, but Twitter acquired a company called Backtype, then improved our Twitter for their use cases. The use cases that I talked about, like how trending topics, what are the popular hashtags and everything, how many people are clicked a tweet, how many people are doing a retweet. So all of that data is getting computed through Storm. That is also Storm is being run at Yahoo. Similar manner, they want to calculate how many financial transactions that's happening in their Yahoo stores, how many people are clicking on the Yahoo front page, how many ad clicks are happening, all of that is running through Storm. Similarly, there are other projects called Apache Spark Streaming, Flink. Now, finally, we implemented something to make the life of developers better by implementing a topology, a UI-based editor to build streaming applications. So I'll get more details into that. So a little bit of Apache Storm, another distributor computing system where you have an inverse, a master like that. Similarly, in HDFS, you can draw parallels to a name node, right? Name node kind of holds all the information about, like a metadata about all your HDFS files and everything else. And then you have a supervisor nodes. where your application gets deployed. Similarly, there is another project of Flink. Flink is, again, a streaming data flow engine that provides you a streaming API along with a MapReduce style API as well. So before going through that, let me show you some, how typically So this is how a application in a Storm will look like. So Storm has a combination of spouts and bolts. That is the API. So spout is a source of events, right? So think of in terms of Twitter, right? Twitter, someone is going and writing something, all of the data getting stored into Twitter's backend, and also the data is getting sent through to a Storm computation queue. The way they send it through is through Kafka right now. Let's assume that is your messaging queue. So pretty much any streaming application needs a durable messaging queue. Okay, the reason for that is you have tons of data that is coming at you, and you want to have some kind of buffer so that your processing engine can catch up. So if something happens to your processing engine or your application goes down, you can still have the data in the buffer. So that's pretty much the common way of deploying streaming applications. So irrespective of if you're using Storm, Spark, or Flink, you will use some sort of queue, be it Kafka, Kinesis, or some other messaging queue. So in this example, what we have is if you can see the code here, it's a constant emit of sentences. This is a word count topology. So you have a spout, that is your API, and there is an array of static strings that is keep getting emitted, right? So that's one thing. That's one part of this topology. Next thing is a split sentence. So you have a spout and you have a bolt. Spout is the guy who is emitting the strings, and bolt is where you're actually doing some kind of processing. So think of spout as someone is tweeting, but think of bolt as where you capture those tweets and try to analyze that tweets, right? For example, if we have 20 people here, 20 people are tweeting about a US Open match or something like that. In the bolt, you probably want to kind of rank them. How many people tweeted about this match versus that match? So that's where the bolt comes into play. So in this example, this is a word count. Word count is nothing but a sentences coming through, right? And you want to split the sentences by a space so that you can separate this, split the sentence to words. And then at the end, you want to count how many words are there, like same words, right? So if you can see here, this simple code which is getting an event. Tuple is your event. It's going through the sentence that's being emitted from here, and basically splitting on space and emitting that again. So each word will get a count of 1. Now, at the end, what you have is a word count, right? So word count is nothing but you're getting all these events coming, tuples are coming in, and you're just taking the same word, how many times it appeared. You're creating a map within that, and just doing a count of those words. So this is your topology, a simple topology on how it looks like in the Storm. So there is a bunch of code that someone has to write, and someone has to kind of make sure this is working together, and go and deploy onto a Storm engine. So if you think of, if you replace, kind of map that into Twitter use case, you will replace this this particular spout with a Twitter spout, for example, or a Kafka spout, which reads from a Kafka and emits the data into your downstream bolts. Does it make sense so far? Any questions? So before, so that's kind of how stream processing, and the problem with this, the current engines is there are Storms, Flink, Spark streaming. Everyone needs to know the APIs in it, and everybody needs to know the complexities of how to develop an application. So what we are trying to do with Stream Analytics Manager is to kind of up-level that. That is, as a developer, you don't need to worry about what's going on the Kafka side or what's going on the HDFS or HBase side. You want to build the application itself. And you don't need to worry about, let's say, Storm APIs versus how Spark APIs works, how Flink APIs works. So we want to kind of go beyond that. So that's the evolution we want to try to get into. So far what's happening is any user who is trying to develop an application, they need to learn about all these different APIs and try to build an application, monitor that application, and kind of make that production ready, right? So on the sideways, I'm going to infuse something called a schema registry. So I'm going to talk about this diagram. So I don't know if you guys are aware of Kafka, any messaging queue for that matter, Kinesis. Okay, any of you? So to give a simple introduction about Kafka is think of it as a queue, but a durable queue that stores the data on the disk. So queue is nothing but you push an event at the end and you pop event from the front, right? So Kafka is nothing but like that, but in a distributed fashion, it's really fast. The reason for anything like Kafka is, as I said earlier, you have all of these events generated. Like Amazon is a big site, a lot of users logs in, there is constant data that is being generated, right? You can't really process in really fast as let's say a Amazon site is working, especially during the holiday season because there is a lot of traffic coming in. So what's happening here is Kafka will help store that data in the order that it came in, so that other systems can pick up. If other systems are slower, the data can still exist in Kafka, right? So it's like going to a shopping counter and trying to buy stuff. So you have people lining up. If the shopping counter is only one person, it will move slow. But if there are more people, it moves fast. But there is buffer, the line is your buffer, right? So that's what's happening in these systems. So what traditionally, as I said, with a streaming thing is you have all these APIs putting data into Kafka like queue, and you have streaming engine at the other end trying to read and process the data. So whatever the activity you are doing in Twitter, Amazon, and everything, all the data going to Kafka, some sort of queue. At the other end, you have Spark, Flink trying to read that and process that and make sense of the data and try to provide some kind of results back to the users. So the data that is going into these machines, these Kafka Kinesis, is bytes. So it's just raw bytes. So nobody knows what's in the data. For example, you are sending a user data about in a JSON format, right? The JSON has like first name, last name, address, something like that. But when you put into the Kafka, it's actually turning that into a bytes and putting into it. So the people at the other end of the queue who is reading doesn't know exactly what format of the data is. So the way that currently happens is, if he's writing data into Kafka and I'm on the Storm side writing an application, I'm going to talk to him saying that, hey, what kind of format you are pushing into it? You're going to tell me that, no, I'm sending as a JSON. This is the format of the JSON. Now I'm going to code that into my application and how to parse it. Now, if he changes any of that format of the JSON, then I need to go and talk to him. If my application is in production, if he changes without telling me, then the application will fail because I didn't know he changed something. So that's where the schema registry comes into play, right? So as you see, there's a producer is being him, like you as user generating data on Twitter or Amazon, and consumer is me who is writing a streaming application to consume the data. So right now it's entirely translated into bytes, which until unless we go and talk to each other, we don't know. So what we are trying to do is schema registry is you can go and define a schema about a topic, about a queue in the schema registry. So he will go and say, hey, for this topic, for this queue called users, this is my format of data. So I'm going to go look up based on that in my code itself. For this topic, give me the schema. Then I'll parse based on the schema. This is all happening in the code. So we don't need to kind of interface anymore each other. So if he goes and updates the schema, he's going to go and register a new version of the schema here, right? And on the back end, I don't need to do anything else because there's a new version coming in. I can look up the data and grab the new version of the schema format and parse it. Does that make sense? So this is how the component architecture will look like. So NiFi is another system which does the flow management. You have Kafka, you have Streamline is what Schema Analytics Manager. So Schema Registry is like another like a web application where you go and register a schema. I'll show how it looks like. Underneath it, we store that data into MySQL or any of you. These are applicable, so you can store it in any of this stuff. And you can also write your own service that can associate with it. And we also have a Schema Registry client that can query the Schema Registry APIs, and you can embed that into your application itself. So that doesn't need to code anything else. You just need to configure the Schema Registry client, and it will take care of the rest of the interaction. So to give a quick demo of that, so these are the existing schemas, right? So if I go and create a schema, here the name is equivalent to what is your Kafka queue name is, so that you're associating a schema text to that particular name. So let's say I want to define a Yelp reviews, because people are coming to Yelp site and they are writing reviews, and I want to process how many people are writing reviews, and I want to kind of generate a real-time dashboard of how many people are liking a particular restaurant, or how many people are leaving a negative rating. How good, what are the top popular restaurants. So if there are a lot of people are liking certain restaurant, that means it's popular. So I want to kind of process that kind of topology, right? I want a streaming topology. So in this case, I'm going to call it as Yelp reviews. Okay. So you can see here, so it's pretty much a spec. What it's doing is, hey, in my Yelp review, these are the fields that might be coming in. One could be user ID, who is the user who's writing the review, and the type of the use, that particular field is string. Similarly, there are a lot of other details here. Votes entry, did they like it, did they find it useful, did they find it cool or whatnot. So this is pretty much defining what is the data that is being getting pushed into the Kafka, right? So I, as a developer, doesn't need to go and code it. Like if you're looking at just passing a bytes, you need to convert that into a string. Then you need to use a JSON, parser to kind of parse it. And I need to know what are the fields that are there, right? So here I'm expressing it here. So anyone who is looking for Yelp service data can depend on the schema. So similarly here, you can, if there is something changed later, you can go and add another version, right? You can add a new field, or you can change the type of the field or whatnot. So in the later stages, if you want to, you're developing this site constantly, you want to add additional details, you can do so. So that's, a schema registry will enable you to not to worry about the data. Everybody knows, like me, especially in a bigger organization, there are multiple teams. They're working on different parts of the system. You all can collaborate based on the central schema repository. So this is how it's, architecture-wise, this is how it looks like. So message store, you can think of it as a Kafka again. So sender is someone is sending the data, like a user's activity or whatnot. So they're already going to talk to schema registry, get the schema, and serialize the data, and put that into as a byte storage into message store. On the receiver side, which is could be your Spark or Storm or Flink, can again read the same bytes, can talk to schema registry, saying that, hey, what is the schema for this particular bytes, and get the schema back and do serializing. So in the end, you have a Java object of Yelp review. So you don't need to do any, parsing or anything manually. So that's, so again, right now the integration that we have is through Kafka, NiFi, and SAM that I'm going to showcase. So it's the UI I looked at. So any questions on the schema registry? Yes. Kafka. Python? Yes. Yeah. That's that's the entire utility of Kafka itself. So yeah.
So this schema file is always in the JSON format.
It's right now we are supporting Avro. That's the Avro format that you saw here. Avro is another format which expresses much more better how the evolution works. The meaning here is, let's say you express the version 0 of this schema here, right? And you set the compatibility to be backward.
Okay, but when I saw this,
it looks like JSON, yeah, but it's it's not just. I mean, the arrangement of the text is, you can call it as JSON, but it's called as Avro format in the sense. How do I explain? For example, we are using JSON as kind of underlying type, but in what we are calling it as Avro. Avro is a library that enables between schemas how the compatibility changes between the versions of the schema. Again, compatibility is another story, right? So these are all in a multiple machines, and let's say you have a schema at the central storage. You wrote the first version, right? And if you said, hey, this is how L preview is going to look like. Go develop your applications, and you have 10 teams who went and developed the applications. They deployed in production. Now, for some reason, you added new data, right? You can't go and change the existing version. If you change that, all of those 10 teams will have to change as soon as you change it, because you're going to produce new data, and all of their applications still on older version of the schema. You get what I mean? The same issue that we talked earlier will still persist. So with Avro, what you can say is, hey, this is the new version. It is backward compatible. That is, if you're using older schema, you can still read the new data. So the reason for Avro here is, it makes sure before you even register that if this new schema is backward compatible or not, then only it will register it. So Avro handles this compatibility really well. That's why we use Avro. But the look of the schema looks like JSON or whatnot, because you can't go anything else then. But the library that we use is called as Avro.
Let's say the user ID field, I remove the underscore.
Yeah, let me see. I have few. Yeah. So there is something called as writer schema and reader schema, right? Writer is anyone who's producing the data. So you depend on one version of the schema. As a reader, I get to choose what version I am compatible with, right? So when you're actually registering a schema, we will ask what compatibility you are choosing. Is it backward, forward, both, or none, right? So backward means, here, let me explain that in this. So here, this is backward compatible. So this is the version 1, right? There are two fields, ID, and there is another field called color. Both are expressed in string format. Now, the version 2 is added. It added a new field, right? But what happens if the version 1, there are 10 teams who are still stuck on version 1, and you suddenly introduce version 2. So there is new data is going in, version 2 data. But the people are still stuck on version 1. So they need to be able to process this new data with a new version of the schema. So when you're registering, you need to mention default is -1. So they'll get that missing field. Does that make sense? So when you write the data with version 2, this version 1 people will ignore this particular field. Yeah, if you don't have that, then you'll get an exception. Yes. Similarly, forward compatibility. Again, forward compatibility means, what if there are 5 teams who upgraded, but 5 teams who didn't upgrade it, and you still have older data coming in and newer data coming in? So forward compatibility means the newer client should be able to read the older data. So that's where forward compatibility comes into play. Okay. Both full compatibility means older clients can read the newer versions, newer clients can read the older versions. So I come to this. Okay. Again, this is an open source project. If you guys have any interest, feel free to reach me. Any contributions, welcome. So that's about the schema registry. Schema registry is a part of bigger things, right? So now you know how the data is. Everybody knows in a company how the data is. The producers knows, the streaming application developers knows. Now, as I told earlier, someone has to develop a streaming application. They need to go write a bunch of code right now, right? They need to understand how these APIs work. They need to understand how the development works. So that's where SAM comes into play, which is called as Stream Analytics Manager. What we are trying to do here is a streaming application is more than a word count program, right? For example, in Twitter case, you have all this data coming in, you're processing it, you're creating a window of a certain time, and you're calculating that. Then you need to store somewhere. It could be HBase, Hive, HDFS, or Druid, so that you can give that results back to the Twitter, so that Twitter can display, hey, this is the trending topics today, right? So those are fairly complex things, because you need to understand where your Kafka clusters are, where your HDFS clusters are. You need to write this code. You need to package it with all the configs. Then you need to deploy and manage. So what we try to do is make that everything easier. So instead of going through slides, it's easier for me to kind of go through the demo first. So we just created a L previews schema, and we already have a few schemas here. So this is Stream Analytics Manager. Okay. So before we anywhere close to creating an application, the first thing what we do is create a service pool, right? Service pool is, you have streaming application is a complex thing that actually interacts with multiple services that you have in big data ecosystem, right? You're reading from Kafka, Kinesis, you're doing processing, then you're doing a lookup on a HBase, or then you're writing to an HDFS file, or then you're actually writing back to a Kafka so that you can enable further use cases. So basically, you are in that application, you are interacting with multiple different services. So what we do here is, so before SAM or any of this, users need to go and check all these configurations, bring them together, and put it in your application, build your Java jar, and then deploy them to streaming engine. This used to happen irrespective of what your engine is today. You could, if you're doing a Flink, you have to do that. If you're doing Spark, you have to do that. Using Storm, you have to do that. So you need to interact with all these services. You need to bring all these configs together. So what we do here is, we already have something called as Ambari in Hortonworks distro. So all you need to do is, hey, this is my cluster. So cluster is something like this. So if you, I don't know if you guys ever looked at the Ambari, but so Ambari is a cluster manager, so it will help you install and manage all your big data services. So this is the project that is running right now. So it's managing Zookeeper, Storm, Kafka, Registry, and Stream Analytics Manager, and a bunch of other services. So when you input that, so we already imported that. So when you input that, it will actually go and fetch all my service configurations along with the services here. So we already created a service which has 3 components in it: Storm, Kafka, Metrics, as well as Zookeeper, as 4. So that's the first step. The next step is creating a environment, right? So in this environment, I want to choose, for example, if you have multiple clusters, right? So you traditionally will have a multiple clusters. You might have a cluster just managing Kafka. You might have a cluster just managing HBase, HDFS differently. So environment allows you to kind of pick and choose the service from different clusters. So I want to choose all this from this. If you have another cluster, it will appear here. You can choose what are the applications what are the services that you're going to interact here, right? So I'm creating my application. Let's call it demo. I'm going to use the environment that I created right now. So now on the side, you can see the toolbar. A topology is nothing but you have a source, again, same thing like Kafka and everything else. If you're Twitter and everyone else pushing in, and a processor, nothing but where your processor, your code will go. and at the end you're going to write to somewhere, right? You're going to write to a Cassandra or HBase or whatnot. So all of these components are already readily available. So all you need to do is drag and drop here. So it will, since we already created the service pool with all the configs and everything, right? It's actually told me where the Kafka servers are and everything else. And it will also show what are my topics and everything else, right? So as soon as I select the topic, I got my schema from the schema registry. So I know what are the fields that are going to be here that I can process. Now let's say I want to do an aggregate of events that are coming in. So I'm going to group by driver ID. So this is like a SQL query, right? It's, window aggregates. And I'm going to say last 5 seconds, timestamp field the processing time. So I'm going to select last 5 minutes. What is the max miles that is appearing in my data? So for driver ID, so I just created a Kafka source. I'm reading the data from Kafka. Okay, I'm not worried about who's putting it. And I'm just aggregating per driver ID. Per driver ID, how many miles that they are driven, or what is their maximum miles driven in the last 5 seconds, right? So you could say last 1 hour or whatnot, right? And I can create a rule saying that so greater than 100, do something about it, right? So essentially what I'm saying is, read, there is data getting generated into Kafka, someone is pushing it, read from it, create a window of data, and add a rule saying, if a condition is met, either I can store in any of these things, or I can send an email saying that, hey, this driver drove really fast, maybe send an alert to him that, you need to slow down, kind of thing. So right. So, I mean, typical email, this long form that I don't want to fill right now. So you can say Kafka. So basically I'm writing to another Kafka topic. So let's go back to the first use case that we talked about, right? So how do we calculate what are the top trending topics that are happening right now in the world? So assume that the data is already in Kafka. That's how it's always been done. Now we open up aggregate saying that, for last 1 hour, give me average, the max number of tweets that happened per topic, right? So we can say per hashtag, what is the maximum number of retweets happen? Does it make sense? Right? So that means that particular hashtag has tweeted so many times. So now you can say in the rule, among all those, sort out the top 10, right? And send that back to, either to the Twitter database or somewhere else. Now you can display a report of what's happening in the world, what are the top trending topics. So that is essentially a streaming application you build. Now with SAM, with Stream Analytics Manager, you don't need to even write a code. You can do this all via UI. And when you hit deploy, it goes and deploys onto Storm right now. So essentially we wrote Storm application without writing any code. The one earlier I shown you is with the code, right? So that's the Stream Analytics Manager. So essentially what you're looking at it is like, how the streaming is evolving. Streaming is going to be the only thing that the data are going to be processed in the next decade or so. The reason is, batch is, you have a stale data that is coming in, you have a data that is stored, you're processing at a scheduled times. Whereas with the stream data, your data is continuously flowing, you're making decisions in the real time, you're acting on those decisions in real time, and telling the users how it's need to be done. So that's the use case is going to be transformed. Now with SAM, you don't need to, we are trying to, help the users think about the business use cases, not worry about the APIs, not worry about how the windowing is created, not worry about the underlying details, right? So that's the solution, the problems that we want to try solve. So I think, to give a little more details about how SAM works is, underneath it is you have a distributed computing engine. You have to have that. That could be Storm today. Right now we have interaction with Storm. Tomorrow we want to build Flink and other engines as well. So we'll be engine agnostic. And you have a unified streaming API. And the stream builder, that is a topology builder that you've seen. So stream builder will go and talk to this unified streaming API. And eventually what you've seen is the deployed version. So it's already deployed here. So you can go my applications. Demo is the one. So we're already reading some data here. So this is actually Storm UI. So whatever we develop right now, so you can see this is the show visualization. So what we developed in SAM is actually this. So already visualized on the Storm. So it's converted all the visual patterns that we built into a code and deployed into Storm engine. Right. So that's what happened when we hit the stream builder to unified streaming API, and then going on to computation engine. Another module that I didn't demo it right now is the Stream Insight. Is a dashboard right now, like similarly, right? So you are doing this application, you want to kind of visualize the data in real time. So another aspect of the SAM is, you build this application, you can store the data into Druid, and there is a dashboard. You can build a dashboard on top of that. So you can actually create, what is your top trending topics, what are your top selling products, how many people are actually bought something, or all these analytics that you can drive through. So this is how the dashboard that I'm talking about. Yeah, so to talk about SAM architecture, it's a simple web server jetty. So you have the UI that we shown right now, which is jetty server has a storage measure, and the first one that we did is to build a clusters, right? You need to have all these clusters that we are pulling in. That is where Ambari is coming into play, and we're pulling it in. And we also have an integration to Schema Registry, because that's what we do, because we want to express the registry, the schema beforehand. So all of this is interacting with each other. When you go and build the topology and hit deploy, it's actually going to the topology action services, which is within the server, and converts the graph that we build into a application, a Storm application, and then gets deployed under to Storm. In the real time also, it's talking to Schema Registry, because it needs to deserialize those events on the fly. So that's overall what's happening inside what we did right now. So yeah, these are all the next upcoming details and everything else. So yeah, that's, I think we still have a lot of time. Yeah, that's about Stream Analytics Manager. Any question that I can answer across Storm, Kafka, Schema Registry, SAM.